QuickCheck can be useful for more than just testing. When we are working with an existing system, which we know or assume to be correct, and we're trying to understand what it does, it can be quite useful to formulate conjectures about what the system is doing by means of a model, and then use QuickCheck or another testing library to verify that this model matches reality. So in today's episode of the Unfolder, we're going to show how we might do this for when trying to understand a library for computing convolutions.
Welcome to the Haskell Unfolder, a YouTube series where we discuss all things Haskell. As always, the show is live streamed, so we invite you to submit questions or comments in the chat, and we'll try to show them on screen and discuss them.
Right, so like I mentioned, we're going to look at a library, and the library is called cuDNN. Doesn't really matter. It's a well-known library for computing convolutions, and we're trying to understand how it works. Now, before we continue, it might be useful to remind ourselves what a convolution even is. Some of you might not have this quite ready. So I'm showing you here a screenshot from an excellent video by Philippe Brown, link in the video description, which if you want to know more about convolutions, I highly recommend you watch this video. But for our purposes here, we can understand a convolution as something that works on n-dimensional arrays. So in this particular example here, it's a two-dimensional array, right? An image, or height by width. And what we're going to do is for every pixel in the output, or every cell in the output array, we're going to look. So in this particular case, we have this cell here highlighted. We're going to look at the surrounding area in the original image or array. And in that area, we're going to have a what's known as a kernel. So this little blue box with values in there is called a kernel. And what we're going to do is we're going to multiply the value of this kernel with the corresponding pixel, and then add them all up. Right? So if all of these values here would be 1/9, 1/9, then the result would be that every pixel would be the average of the 9 pixels in the area. Right? And if, for example, that middle value would be slightly higher and the surrounding value is slightly smaller, then the effect is that we give more emphasis to the original value of the pixel, but we also mix in some of these surrounding pixels. And the result is a blurry image. Right? And this is a two-dimensional example, but this is we can generalize this to n dimensions. And by choosing different values for this kernel, we can do blurring, we can do edge detection, we can do all kinds of things. Right? So convolutions are a very useful tool. That's all we need to know for this episode about convolutions. We don't need to know more than this. Like I said, if you want to know more, please refer to the Philippe Brown video. It's excellent. Okay, so now just to show you how we do a convolution in cuDNN is a lot of work, right? We have all kinds of parameters. We need to have all kinds of setup, configuration, setup, more setup, some preparation, and allocation of memory, copying, etc., yada, 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 right? The point is we don't want to understand this here, right? We want to treat this as a black box and instead focus on how we could conjecture how this might work. And we're conjecturing this is computing a convolution. And then write simple Haskell code that is not necessarily intended to be efficient, but is intended to illustrate what's happening and that we can then compare it to the system. So let's start with the actual development then.
Do we have an entry point that we're aiming for or something like that? Are you explaining the binding to C? No, probably not.
No, not at all. Yeah, not at all. If you want to know more about that, then there's 2 episodes I think we did. One was about FFI in general, and we also have an episode about CUDA, which talks, and this is another CUDA, another library in the CUDA space. So that will be a useful library to watch. The entry point that we're going to talk about is this guy, right? So the main entry point, this is the Haskell entry point into the library. It's going to take 2 tensors, 2 4-dimensional tensors in this particular case. One is the kernel and one is the input, right? One is and the kernel being this little blue box here, right? Yeah. So this is the function we want to test.
Re-implement.
Yes. Yeah. That's right. Yeah. That's right.
Okay.
Okay. Cool. So yeah, that was a good question. So first of all, we need a definition of tensors, like multi-dimensional arrays. And if we look on Hackage, there are multiple ones, but they are all designed to be performant and all kinds of which yeah, I make it sound like a negative. Of course, often that's what we want, right? But when we're talking about testing or modeling, simplicity is better, right, than performance. We don't really care about performance. We want something that is very simple.
Clarity, right?
Clarity, yeah, exactly. And so we're going to model a tensor, an n-dimensional tensor, simply as lists, right? So 1 dimension would be a list, 2 dimensions would be a list of lists, 3 dimension, a list of lists, and so forth. So how do we do this succinctly? Well, we're going to define a tensor. So n is going to be a natural number at the type level, indicating the dimension, and a is the type of the elements. And then we're going to define a 0-dimensional tensor, which is just a value, a scalar. Sorry, I've called it scalar. So that's just an a. That's a 0-dimensional tensor. And then for an n-dimensional tensor, n+1 dimensional, we have a list of n tensors, n-dimensional tensors. So here. And we're going to find it useful to have some extractors here. So I'm going to call this get scalar, and this one get tensor. And these are total because one only works on z and 0, and the other one only successor. So they are mutually exclusive.
Okay, yeah. There's a little bit of type level stuff going on here, and we're using this. This is not from base, right? But this is from Oleg Grenros's Fin and Vec packages, I think.
Yes.
Right?
Yeah. So yeah, exactly. So this is coming from Fin, and this is coming from Vec. We'll use it later. Yeah, these are both of Oleg's packages. Yeah, that's right. Yeah, this is not a. I'm assuming that this type level stuff is understood. We have other episodes on that particular topic, and I'm sure we'll do more. There's also, now that we're talking about this, a link in the video description to a video by Richard on the Tweak channel, our colleagues at Tweak, which talks a lot about like a very gentle introduction to type level natural numbers, vectors, and singletons, all of which we're going to use in this episode. So if that's all new to you, then you might also want to give that one a watch.
Yeah, but it's still not extremely central, I think, to the development. I mean, it's being used, but yeah, I mean, we are not going overboard with the type level stuff, I think.
Yeah, I would like to think so too. Yeah. Hopefully, if you squint a little bit, then hopefully you can make sense of this, even if the details are a little bit on the fuzzy still. Okay, so we wanted a bunch of instances for this, and we can just get them for free. We want show, equality, function, traversable, and foldable. We just all of these can be derived. We had an episode, the last episode, I think the most recent one by Anders, was talking about this. So if that's something you're interested in, you can refer to that one. Just to show an example, it's always useful to have an example. Let's define like a kernel for blurring, like we had in the 3 blue 1 brown example here. So that here's just an example. This is 2-dimensional tensor, right? So we have a list of lists of scalars, numbers, and here I just said 0.1 for all the outer pixels and then 0.2 for the inner one, right? So we have 8 times 0.1 and 1 times 0.2 is together they add up to 1, which is what you want. So.
And here, this is also why I'm saying we're not going overboard with the type level programming. We are assuming that the inner lists are all of length 3, but we're not enforcing that, right? I mean, that they're all of the same length.
That's right. So there's 2 invariants that we're depending on. One is that every list here is the same length. That makes that this tensor is like rectangular. It can't have like a hole in it like this, right? And the other is that none of these lists are empty, right? So you can't have an empty dimension. Yeah, exactly. Okay, good. So let's define a couple of simple functions here, just to get a bit of a feel for how this thing is working. So one thing that we're going to find useful is sort of like a singleton tensor, which increases the size. So if we have like one tensor of size n, we can make a singleton tensor of size successor of n simply by wrapping it in a tensor constructor and then create a singleton list. And we also it's also going to be useful to have the opposite, right? Where if we have a tensor of size n+1, we can get a tensor of n out of it just by getting the one and only element at this level here. And then one other function that's going to be very useful is to compute the size of a vector. The size of a tensor. And the size is not its dimension, it's like how many elements at each dimension, right? And so for an n-dimensional vector, that will be n values, and that's where we're using Oleg's Vec package in this case. So it's a vector. And the definition is rather simple, right? So if it's a scalar, well, then there's nothing to say, like there's no size to give. And for a tensor, we just need to find out how many elements we have at this level, which is just the length of the list, and then we recurse. And now it doesn't matter because we said this thing is rectangular, right? So we just pick one at random, essentially. We just pick the first one and just recurse. Few more simple examples. One is replicate, right? replicate for lists was an integer, an element, and gives you back a list of that length. Here we get a size and an element, right, and it gets you a tensor of that size. The definition is simple. If we have v0, then we want a zero-dimensional tensor, which is a scalar, and so it's just that single value. Otherwise, if we want n values at this level, well, then we use the list replicate to replicate n subvectors. And then which are the subvectors? Well, that's a recursive call to our replicate on the remainder of the size.
Yeah, that makes sense.
Okay, good. So 2 more simple functions, and then let's get into the heart of the matter here. So, and I'm defining these partly to get used to this data type, but also partly because we're going to need them in the other development. So the remaining functions I want to define are zipping and mapping. So zip takes a function from A to B to C, just like zip on lists, a tensor of A's, a tensor of B's, and it's going to give us a tensor of C's. And this is like this. The types almost dictate exactly what this thing is doing, right? So if it's 2 scalars, well, we just apply the function. If it's 2 tensors, we then use the list zip with function with the recursive call to ourselves to zip the subtensors together. And then finally, map, right? So we already have one kind of map, right? Because we derived foldable. Right? So that means
functor.
No, functor. Sorry, functor.
No.
I beg your pardon. Yeah, functor. So since we derived functor, we can fmap over it, which would do something with the A's, the elements here. What I would like is a function that actually works on the nested tensors here. So if you imagine, for example, like we have maybe it's a 2-dimensional tensor and it's an image, height by width, then maybe I want to do something for every row in the image, something like this. And so the definition is very simple. We get a function and a tensor of x's, and then we just list map the function over our tensors here. The only slightly interesting thing here is that our tensors have a dimension n, the subtensors. That dimension could change, right? For example, if we have an image and we do something for every row in the image, we might summarize that into a single value, right? So then we could have 1-dimensional tensor and out at the end. So the dimension might change. So in which case, we start with an n plus 1, and we end up with m plus 1, where m is the result of the function. So just as an example of map, right, we might get a 1-dimensional tensor of values out of this. And by the way, I should have mentioned, test value here is coming from my own package, testing tensor, which is basically a much more elaborate version of what we're developing in this episode here. And it's kind of, think of it as a float, but with a more relaxed eq instance, so that when we compare our model to the real system, we're not worrying about rounding errors. That's basically what this is doing. But to a first approximation, it's a float. Okay, so suppose that we take our blur tensor, and then we sum every row and make that a scalar. Then we get a 1-dimensional tensor out of this, where the first element would be the sum 0.3, then 0.4, and then 0.3 again. Okay, that's basically for the simple functions. If there are no questions, then let's move on to convolutions.
No questions so far. No?
Good. Okay, great. So when we do convolutions, then we need, for every pixel here, we want to look at the corresponding area of the image, right? Maybe let's look at the blue one here. And take that part of the image and then combine that with the kernel, multiplying every corresponding values and then adding them all up. So what we could do as a first step is compute a tensor of tensors, where at every location, say for example for this blue one, the tensor that we get at that location is the subtensor of the original one that is exactly the part that's relevant to compute that pixel. Because if we had such a thing, such a tensor of tensors, then all we would have to do then is fmap over this thing, take every single subtensor, combine it with the kernel, reduce it to a single value, and then that will be the result of the convolution. Right? I hope that makes sense.
Yeah, I think so.
So we can do something slightly similar for lists as a starting point. So I'm going to call this consecutive. So think of this as if you want, as a one-dimensional tensor, right?
Mm-hmm.
And what I want is if I do like 1 to 6, the list 1, 2, 3, 4, 5, 6, and I take 3 consecutive elements, then I have this one, right? This one,
Mm-hmm.
this one, and this one, right? And that will be those subtensors in this one-dimensional tensor, right? I mean, if we would do a convolution over this, and the kernel would have size 3, those will be exactly the areas of the tensor that would be of interest.
Mm-hmm.
So consecutive of 3 of this list should be exactly that. Now, for reasons that we'll see slightly later, is that it's also going to be useful to ask how many of those lists we want. So if I want all 4 of them, then I expect to get exactly the list that I was highlighting just now.
Mm-hmm.
So this is what we'd expect to get.
Mm-hmm.
Okay, so we get 2 integers. One is how many sublists, then the length of each sublist, and then the original list, and then we get back a list of lists here. So I'm going to call this R and N. Now, how do we do this? It's actually quite simple. We take the tails of the list. So the tails is the full list, then the first tail, then the tail of that, then the tail of that, then the tail of this, then the tail of this, right?
Mm-hmm.
That's all the tails. Then we map take over this, right? So now we get sublists of exactly the right size, and then we just take as many of those as we want. And that's our
Yeah, so I mean, we are not, like, because take is permissive, right? We're not getting, after the map, we're not getting only sublists of the right size. We're getting some smaller sublists at the end.
Yes.
But the extra take will effectively ensure that we're only taking the ones that have the right size.
Yeah, that's right. If we would ask for too many, then the next one would be 5, 6, which would no longer be of length 3. Yeah, exactly. Yeah.
So normally, like the 2 numbers, the 4 and the 3, should always sum up to the number of elements in the list plus 1, right?
Yes. Yes. Yeah. Okay. So to define our convolution, remember that we want this tensor of tensors, right? Just like this consecutive gives us a list of lists, now we want a tensor of tensors. And for list, we wanted a single number. I mean, with this additional thing here, which is the size of the list. So for subtensors, we want a size, which is a vector of numbers, right? So subs is going to have this size, which is the size of the subtensor that we're interested in, which would equal the size of the kernel, right? When we do the convolution. So then tensor of A's, and we're going to get back a tensor of tensors of A's. Now, I'm going to leave this undefined just for now. Just to show you that convolutions are then extremely simple once we have this.
I thought you were going to say you leave this as an exercise for the audience.
No. Although if you wanted to pause the video and try it for yourself, I'd recommend it. It's a good exercise, but no, I will show you how it's done. But before we get there, let's just first show that convolutions aren't that easy. So if we have a tensor of A's, which is going to be our kernel, and then another tensor of A's, which is going to be our input, think of it as the image, right? Then we're going to give you back a new tensor of the same dimension, again of A's. So I'm going to call this kernel and input.
And here there are again sort of like additional invariants, right? I mean, this kernel tensor has the same dimension, but it must have sort of in all components a smaller size than the input, right?
It doesn't make sense to have a kernel that's larger than the input. Yeah, because then you'd want to sum up values that you don't have. Yeah, that's right. Yeah, that's correct. Okay, so first we're going to compute our tensor of tensors, right? So we're going to use subs. How big should those smaller tensors be? Well, they should be the size of the kernel. So now each of them is exactly the size of the kernel, provided that it's not too small, right? That's what Anders was just saying in the input. Now this is, if I look at my HLS here, is a tensor of tensors now. Okay, so we can map over this, fmap over it. So now we're going to fmap over each of those smaller subtensors here. And I'm going to call the function that we're going to fmap over this just some auxiliary function. And the auxiliary function needs to take one of those.
And this is using the fmap on tensors, not the map.
That's right. That's right. Yeah.
Exactly.
So this is fmap if you prefer. If that's clear. Yeah.
So just a standard mapping over the elements.
Yes. Yeah, and which are tensors in this case, because we have a tensors of tensors. Yeah, it's slightly confusing perhaps. Yeah. Okay, so so we have one of those subtensors and we need to return it into a single value. Well, remember what we were going to do when we were computing a convolution, right? We just multiply the corresponding values in the image and the kernel and then add them all up. So that's extremely simple now. We're just adding, we can just sum because we have foldable. And then to multiply the corresponding entries, we just zip with multiply. And that's basically it. Now we need to have a num instance on A. For all A. And that's it. All right, so once we have subtensors, defining the convolution is very simple.
Yeah.
Okay. So let's think about subs now. Now, let's start like this. We're going to have a kernel size, and the axis, the input. And I'm just going to call a local function on both of these. Right, we'll see in a second why I'm doing this in a slightly weird way, but okay. So we have the size that we want. We have our input tensors, and we want a tensor of tensors. Okay, so if the size is nil, right? Remember this is a vector, right? So if the size is nil, that means that we're now dealing with the zero-dimensional case, which means that this tensor must be a scalar, single value. And now here we want a scalar of that value. So okay, we just do that, right? There's very little to do here. Now, if we have some size that we want, a tensor, then we are told at this level we want subtensors which are like size n at this dimension.
Yeah.
Okay. So we need to make a tensor. We know that. And now what we can do is we can recursively call ourselves on the rest of the tensors, right? On the we have a list of those. So we list dot map go on each tensor, right? So now for each subtensor that we had, we have now a tensor of tensors, and we've listed those things. And now we want to construct the appropriate consecutive subtensors at this level, right? We want to pick the first three, then the next three, then the next three, and so forth. All right. So we can use the function on lists that we had for that.
The consecutive function, you mean? Yeah.
The consecutive function, yeah. So let's do that. So I'm just going to use a list comprehension here to do this. So I'm going to call these selected. So consecutive. And now we need to compute how many we want. I'm going to leave this blank for a second. Then now the length of those sublists, that's n. And then what we want to select them from, right? So, okay, good. I'll leave this undefined for a moment here. Oops. Okay. Now, what is selected here? It's a tensor of n of tensor of n of a. Okay, that's looking good. And a list of those things. And we want to have a tensor of n of tensor successor of n of a. Right, so in a way,
a single yeah. So we have a list of those tensors, and we want a single tensor, but one which in the inner dimension is one larger. Yeah.
Yeah, that's right. So intuitively, we need something of a higher dimension here, right? And intuitively, that list gives us that higher dimension.
Yeah, because a tensor of successor of n, if you expand that one level, is effectively just a list of tensors of n2, right? So we're just pushing the list further in, right?
Right. Exactly. Yeah, exactly.
Yeah.
So we want to push this list in one step. So now we get a tensor of list of tensors. And then we can turn it into a tensor of tensors of one dimension larger by using the tensor constructor. So let's abandon ship for a moment and think about how we could push that tensor, that list constructor into the tensor here. So I'm going to leave this undefined for now. So what is it that we need? We have, I'm going to call this just strip. We have a list of tensors. And I want to push that list constructor in to the elements here. Now, if you look at this, and you've been a regular like a viewer of the Unfolder series, then you might recognize this as being from the distributive package, right? We had an episode, a couple of episodes ago, where we talked about distributive, and this is exactly that. Now, we said at that time that distributive doesn't really work for list or maybes or anything that's a sum type because we don't know, like we have too little information. And to make that slightly more clear, let's generalize this type slightly to an arbitrary functor at the outer level. Right? So here we have lists, but we could generalize this to an arbitrary functor f. And now the relation to that distributive becomes even more obvious, right? But we have some f of a tensor, and we need to produce a tensor, right? And this is, we don't really know how to do this because we could take a look at... Yeah, go for it.
The idea of distributive is that you know the shape of the resulting thing more or less exactly, right?
Right.
So you know the thing that you want to produce. If you know the shape of what you want to produce and you have this functor of things that contain things of the same shape, then you can simply produce the whole shape, right? And then create every one of the elements by selecting the right component out of the functor application by f-mapping an appropriate selector function over that functor. That's the idea of distribute. But that only works if sort of the shape is completely a given, and it's not really dependent on the f. So that's why I was slightly looking confused when you were saying that the f is a list is not the problem, but our tensors are, at least as far as the type system concerned, they are giving a lot of freedom, right? Because we don't know the length of the lists in there, and exactly.
Okay, thank you. That's a great explanation. Yeah, exactly. So Andrew said we can do this if we know the full shape. We don't know the full shape because it's not available at the type level. But if you tell me what the size of this thing is, then we do know the full shape. So then we can exactly do what Anders is saying, right? So, okay, we do require f to be a functor. And then if you tell me what the size of the resulting tensor needs to be, then I do know what the full shape is. And now I can actually define this. So if that size is v0, then it's a scalar. Okay, so that means we need to get a scalar, right? We need to produce a tensor of size 0. Okay, that's a scalar. And what do we have? We have an f of a scalar, right? So we can just f-map get scalar to get that scalar out of it, right? So that's quite simple.
Yeah, and this is the general principle that I just said. You produce the shape and then you're extracting the components, only that in this case you have just one, right?
Right, yes.
But
yeah. So if we have an actual tensor, right, a non-scalar tensor, then it needs to be a tensor. And we can do the same shape again, right? It's get tensor. But now we have an f of list of tensors, and we need to get a list of tensor of f's. So there's two distributions going on, right? First, there's the f, there's the list, and there's the f. So we could abandon ship one final time, increase the stack, and first think about how we might do this for lists. So I'm going to call this just strip list. And here it's the same thing, right? We cannot define this function, which would be distributed for list, because exactly the shape of this list is not known just from a type, right? So we can't.
Yeah, and also it's not guaranteed normally that all the lists that occur within f have the same length, but it's an assumption that we here make, right?
Right.
Make that like sort of all related lists have the same length.
Yeah, exactly. So if we are told the shape of that list, which in this case is just the length, which is just a number here, well, then this function is definable, right? So if that length is 0, well, we need to produce an empty list. Okay, that's easy. We can do that. If it's not 0, then we need to produce something here, right? And then in the tail case, it's just a recursive call. Applied to what? Well, we have the tail of this guy here, essentially, right? But this is f of a list, okay? So, but we can just map tail over that thing here. And then here, it's the head of this thing, right? And so we map head over that.
You missing the functor f constraint. Yeah.
Yes.
Yeah.
Okay, so now we have distribute for lists. Then we can now do the distribution for tensors because we had that double distrib going on. So we can first distribute for lists. Sorry. And now we have a list of f's of tensors, and we need to have a list of tensor of f's, which is exactly distrib here, right? So now we can just do a recursive call on ends.
Fmap
of that thing, yes. Yeah, and this fmap is it's a list of map essentially, right? It's the same thing. It's the mapping. Over
that's the map function on lists.
Yeah. Okay.
This is also, I mean, this can all be potentially, right? It's a trade-off. I mean, if you can make everything more typed, then you have other problems. But one of the good things that comes out of that is that you could actually define the distributive instance for this, and then this composition of list.map of distrib ns after distrib list of n, that would just be sort of the composition of two functors is also distributive again, right? So and that would just follow from that. I mean, basically, if you look at the distributive instance of the composition, it is just exactly this list.map distrib after distrib. Sorry. Sorry for that.
Thank you for that. Yeah, exactly. So we're not tracking the sizes because it's a useful exercise to do it, and you find that some things get more complicated, but yeah, we do get some benefits also. But yeah, there's always a trade-off, right? Like how much information do we put at the type level versus how much do we use at the term level? It's always an engineering trade-off. Okay, so now we're nearly done. We had this selected here. This was a list of tensors, and remember the idea was that we wanted to push that list in, and then
using distrib,
which we can now do using distrib. Now distrib wants to know the size. We don't know the size yet, so let's leave that undefined for now. And now we have a tensor of list of tensors, and we want a tensor of tensors, but for a higher dimension, and that's just literally just the tensor constructor, right? So we can just map tensor over this. Okay. So the final piece of the puzzle, the last undefined here is these sizes here, right? Both to distrib and to consecutive. And so we want to compute the size of the subtensors. So if we have a size of the kernel essentially and the size of the input, we want to know the size of the result, how many subtensors are we going to get? And that's relatively simple. If these are scalars, then there's no size to give at all. And if at this level we have a kernel of size k and an input of size I, then we are going to get an element for every I elements, right, in the input, except that the last few won't have sufficient number of elements to make up k, right? In this list example, where was it? Here, we had 6 elements here, but only 1, 2, 3, 4 elements in the result, right? Because 5 would only, if the list starting at 5 would only have 2 elements, and the list starting at 6 would only have 1. Right, so the number of elements that we're going to get at every level is I minus k plus 1. That's relatively simple. And then we just recurse for the rest. Okay. And so now finally, we just make this an additional argument to our Go function. We just compute ahead of time what the size of the output is going to be. And we just make that an additional argument here. And now the recursive call, that's the R's here. And now this is exactly the information that we want. The R is how many elements we want at this level, and the R's is the size of the sublevel, so that's what we need as the argument to the string. And that's it.
Yeah.
Okay, good. So
I think you probably want to do this anyway, but I think like at least some in the audience have lost the big picture at this point because I've already tried to answer this on the chat, but I think it is a good time to kind of recap why we're doing this, right?
So this is so we're going so thank you for the question, and we're going to get that right now. So the point was that we might have some big system, and then we're conjecturing some properties about that system, and we're going to conjecture it as a model. And in this case, the model is what we just defined. Like we wrote the model for convolutions. And then how do we then check our conjecture as well? We're going to use QuickCheck to verify that model, right? Not to test whether the system works correctly, but whether the model works correctly. And whether you use QuickCheck or Hedgehog or Falsify or anything else, that doesn't really matter. But some property-based testing framework is very useful here.
I'm tempted to see whether our tests catch this, but I think another member of our audience who was more alert than me and you, I think, just spotted an actual bug.
Oh, thank you very much. Thanks, Liam.
Thank you.
Yeah, it would be interesting to see if the test would catch it. I would be very disappointed if they don't, but I'm also not that's not really the focus of it. But yes, if we have time, we can take a look. But thank you for that. Yeah, that saves me some embarrassment later. It's always appreciated. Okay. So let's now actually get to the QuickCheck part, right? How do we now verify that that this thing is actually matching the implementation here, right? And to do that, we need to generate arbitrary tensors, like random tensors. Otherwise, we can't do random property-based testing. So we need to have an arbitrary instance for tensors. And I'm going to do one which is really rather simple here. So we're going to only test against the blur in this episode, only against the blur image, the blur kernel. We're not going to generate an arbitrary kernel. We could, but it just other complications. So we're only going to generate a random input. And so, like Anna said earlier, the input should be at least as large as the kernel. So we're going to generate a size for the tensor first, and dimensional. And we're going to use lift arbitrary here. So lift arbitrary just takes, like, for any functor that supports it, just takes, give me a generator, and I'll give you a generator for the larger thing. And we're going to choose something of least size 3, because our
so these simplifications are for the purposes of the episode, right?
Yes.
Because it's already long. But you in your library, you don't have any of these limitations, right? That's
right. Yeah. So there's a link in the video description to the testing tensor library, which has quite a sophisticated arbitrary instance, which doesn't have any of these. So this is just to keep things simple for now. Yeah. Right. So once we have the size, we just replicate. That's one of the functions that we wrote earlier. We create a tensor of actions which generate arbitrary values, and then we just sequence all those actions to get the tensor. And then finally, the shrinking, I'm just going to omit altogether this episode. Again, the library has a quite a sophisticated way of shrinking.
Nevertheless, it's a special day when ETSCO deliberating shrinking.
yeah, I do feel sad about this.
You're still getting errors there. Why is that?
Yeah, I'm getting errors for 2 reasons. One is that we are generating arbitrary values, so we need a way of making arbitrary values.
Of course.
So that's doing that. And the other is that this generates an arbitrary vector, and to do that, we need to know at the term level what this n is, and that means we need a singleton for n. If that makes no sense to you at all, what I just said, it's not really all that important for this episode. The video that I linked to on the Tweak channel by Richard explains that in detail. So that's a good reference there.
Yeah, I think we also probably mentioned singletons already at some point, but yeah,
we have.
Richard is an expert world expert on singletons.
Yeah, and it's a nice series. Yes.
Yeah.
Okay, so now Anders asked at the very start, what's our entry point? And I said this is our entry point, right? And this takes 4-dimensional kernels and inputs. So so our first conjecture might be that that should just match, right? We just do a 4-dimensional convolution. So I'm going to call this prop4d. So we have a random, a 4-dimensional tensor of test values, random floats basically. So this is going to be our input. And I'm just going to say that if we use the model, it should just be the same as using the actual system here. And so the kernel using the model and using cuDNN should all have 4-dimensional tensors. Now our blur kernel has only 2 dimensions, so we can just use our inject function that we wrote to make it larger, by having singletons. And we need to do this twice because we need to go from 2 dimensions to 4 dimensions. So I just inject twice. And then using the model would just be tensor.convolve kernel input. And using cuDNN, it's the same thing, right? And that's it. So this is our conjecture. This is how convolutions in cuDNN work. So let's just verify this conjecture by verifying this property. And let's run this. Building should be quick.
Oh no.
And it fails.
After one test.
After, one out, actually.
One out of one.
After one test, exactly. So the first test failed. And in fact, if we run this and we tell it only take one, QuickCheck normally tests 100 tests, right, or whatever per property. If we say only run one at 40, then it fails immediately, right? They all fail. So it's not something subtle, right? It's not like, oh, for some examples it works, other examples it doesn't work. It's not something subtle at all. Something is broken in our understanding of how the system works. And at this point, we could go back to documentation and see what we're missing here. And it turns out that although in cuDNN, these are both 4-dimensional vectors, it's not really how it works. It's not a 4-dimensional convolution. Instead, the 4 dimensions in cuDNN this is done for image processing. The first one is images, and every image is done independently, basically. And then the next thing this in the input is channels, red, blue, green, and then height and width, right? The kernel is also 4 dimensions, not because it's a 4-dimensional convolution, but because it's a 3-dimensional convolution, channel, height, and width. And then it's an independent convolution for each of those outer dimension of the tensor. So if you have that first dimension, you could have I don't know, a couple of kernels there, and they're all done concurrently on your graphics card, right? But it's not a 4-dimensional convolution, and that's why this is not working at all. And if we were to look at these examples, we would see that since we have only one kernel, effectively, the results only in CUDA is always going to be one output, one channel per image, whereas in a 4-dimensional convolution, that's not going to be the case, right? Put another way, in cuDNN, a proper 4-dimensional convolution would be able to combine values from different images together, right? That would be the first level of that dimension. You cannot do that. Every image is done independently. Okay, so this conjecture is falsified. So let's make a new one, and I'm just going to paste this in because it's quite similar. So let's simplify slightly. So this one we expect to fail. This is not true. But this one, so here we only have 2 dimensions. Let's focus only on the first 2 dimensions. So now we have one image, one channel, right? And so we are using a model. We just literally convolve these directly. There's no need to inject a project because the blur has the right dimension. And then for CUDA, we inject both the input and the kernel, and then we project at the end to get the result back. And if we test this, And oh, we're not actually calling this. That would help. Yeah, so that passes. And we can make this a little bit more explicit, and this is the final thing I will show, is that, so I said that in cuDNN, all these images, like the first level of that, like that mention, the first dimension, is all done independently, right? And so we can make this very explicitly using our model. And so now we have a 3-dimensional input value here. And so we're just inject and project just to get that from 3 to 4. But our model here, our definition, our explanation, if you like, is very explicit here, right? We're going to map at the first dimension. So in meaning, we're going to process each image independently. We're doing independent convolutions. What are we mapping? A regular convolution. So this makes it very clear what's happening in this library. And so when we are testing this, hopefully that will also pass. Let's just check. And indeed it does. So yeah, that's basically that's all I wanted to show today. Are there any final questions?
There is a comment by Magnus, but I'm wondering whether he means what he wrote. So what I encountered in practice is that I had a nice model, but the fast implementation was
I'm assuming he means exponentially faster.
Yeah.
I'm assuming he means faster. Yeah, exponentially faster than the model, so not could feed useful enough examples.
There is like a follow-up. Are there useful ways of figuring out when to use? Yeah, okay, so he confirms he means faster, and he said, are there useful ways of figuring out when to use difference testing like this, and how to come up with useful models?
So it's not been my experience. I mean, you're absolutely right, of course. What we defined here is going to be exponentially slower than the real thing, right? Not only is the real thing written in C, it runs on GPU hardware, it's designed to be blazingly fast. This is all running on one core with like pointers, like the lists are linked lists, like everything is nothing optimized for speed, right? Everything's optimized for clarity here. So of course, yes, it is going to be way, way slower. It's not been my experience that you will only see differences with large examples. If that is truly the case, then you need to think about performance in your model. I would, in most cases, I would try and then, like for most systems, there's a concept which is like design for testability, right? And so if your system, for example, generates tables, and those tables have like 1,000 entries in them by default, right? Make that number 1,000 a parameter. So you could set it to 5 or 2 or 3, right? Something small. Right, so which is not something you would ever do in production, but by having those kinds of parameters, you ensure that small counterexamples will be sufficient to test your system. Right, so I would like if this is what Magnus is describing is really the case, and you cannot modify it, then yeah, you need to make your model faster. But I would try and encourage you, and in my experience, this is always possible. Of course, it's not possible if this is an external system, right? So maybe in the context of this particular episode, if it's a CUDA or whatever, then maybe this will be difficult. But if it's a system that you have some control over, try and design for testability so that if there are only counterexamples that are large, try to parameterize your system so that you could come up with smaller counterexamples. Yeah, so that's, I guess, what I would say to that.
Yeah.
Anything else?
No, I just wanted to reiterate one more thing. I mean, because like perhaps the discussion in the end went a little bit away from this, right? I think the main motivation of this was very much what we showed, like with the, like you could easily jump to a wrong assumption about what a library is doing, even if you're fully assuming that the library is correct. Because like if you have an interface like these 4-dimensional vectors and a function that is called convolve, you might just assume it's doing one thing, but it's in fact doing another thing. So this failing property that Etzko showed initially, I think this is a typical example for something that could really usefully happen in such an investigation, right? So you've come up with a model and you figured out that, like, I mean, right, there is a mistake, a conceptual mistake, which is not even because you made a mistake in your implementation or the library is wrong, but just in your understanding for what a particular function is doing exactly. And that's, I think, very much why this stuff is useful, right? And because it's much harder to get these things all correct up front, or if you silently build other code on this wrong assumption, you'll get your mistakes at a completely different level where they are much harder to debug or experience, right? Because they're intertwined with lots of other code. And doing something like this is of course a lot of work, but can really help the understanding.
Yeah, and I would argue, like, we did this in 50 minutes now. Right? Yeah. And the real library is not much larger than what we did here. So, I mean, a lot of work is also relative, right? It's a couple of hours of work for a serious implementation. So, yeah. But yeah, overall, yeah, I completely agree with that summary. Thank you. That was couldn't have said it better myself.
Yeah, so thank you for watching this episode of the Haskell Unfolder. If you enjoyed it, please like and subscribe. And as usual, we leave the chat open for a little bit longer, and afterwards feel free to leave further comments in the comments under the video. And yeah, we'll be back in a couple of weeks again. Thank you very much.